Okay. Well, welcome everybody. Well, good morning, good afternoon, good evening, wherever you are in this world. It's early here on the US West Coast. So I saw we have like almost like 150 folks here in the room. That's wonderful. Today, yes, we'll be talking about building embedded containers with the Yocto projects and embedding those into our root file systems. Okay, I apologize. There's one mistake on these slides. I forgot to adjust the date here on this one. I did a similar talk about a year ago, but now this is of course the very much improved version of it, so to say. And maybe a little bit about myself. My name is Streif. I'm a consultant contractor. I have a consulting company in the United States, doing all types of mostly embedded work with open source and Linux, but also other things such as security for systems for automotive and things. We have well, quite a slew of customers, including Toyota, Mercedes-Benz, or Jaguar Land Rover a while ago, automotive customers, a company that makes like aerial devices, trucks for with buckets to lift up high, all of these, and a company that makes appliances, essentially high-end kitchen appliances, where we developed the hardware and the software actually for a connected oven with the Yocto project. I've been with the Yocto project quite a bit. It started in 2010 when I became the director of embedded solutions at the Linux Foundation, and so the Yocto project just started taking off, and at the time I was the Linux Foundation representative for the Yocto project. And ever since I started with the Yocto project, it's a great thing. It's a great team, and lots of wonderful work has been done in so many years. Shout out of course to Richard Purdy and as the technical lead and all the other on the team. It's wonderful, excellent work. And every year in these summits, I'll do a little bit, hopefully, a contribution to those by talking about a couple of things and giving some tips and ideas what can be done, maybe a little bit outside of building standard images and things like that. All right. Here we go, scroll down. So what we're talking about a little bit. So we're talking about virtualization. Containers are virtualization technology. Essentially, there are others. We'll go into that. We're going to be setting up our class environment. Pretty much everything is already prepared. You have your virtual machines, thanks to Maite Halstead and also to David Arena, who made this all possible. And quite frankly, well, big shout out, makes it also easy for me as a presenter actually to do this. We're starting off next with the Hello container, the container variant of the Hello World aspect. We're building a system with the Yocto project that actually can run containers, and we're just running a basic container on that one. Then we start looking to building containers with the Yocto project, and then embedding containers from a registry, so an upstream registry. So the first step is we're building the container also with the Yocto project, which of course is an option you can do, but you can also leverage work that already has been done by using containers from registries such as Docker.io. And last but not least, we're kicking it up a notch, and we're building containers with Docker Compose, actually building a multi-container application, 2 containers that will actually work together. And of course, we'll go into those details. And every once in a while, I need a sip of coffee so I can keep talking. Each of these sections will have an introductory part, essentially. And then we dive right into doing it hands-on. The hands-on doing may take a little while here and there to build something. And while we're building, it's always a good time to ask any questions that you have. So I appreciate any questions. And so and I'll try to keep my eye out on the chat for questions to respond to those. All right, virtualization technologies. Here they are: hypervisor, emulator, container. What actually are those? Right. Maybe you're already familiar with those. So virtualization, it's actually a technology process for sharing resources, hardware, software, data with multiple different environments. Each environment runs in its allocated resource space. So you can allocate processing power, you can allocate memory, storage, I/O, and you can also curtail the virtualized environment's usage of these resources. You can say, okay, this virtual environment can use 2 CPU cores and 4 gigabytes of RAM and gets that much disk space. So this is all possible. And to set this up. And of course, it's important. It is also very important for resource constrained systems like embedded systems in particular. In a virtualized system, there's 2 terms often referred to as it's the host, which is actually provides the virtualized environment. It is the one that is actually managing all of the resources, and it's also responsible for the arbitration between the different virtualized environments that it actually supports. And then there are guests. These are the virtualized environments, the virtual machines, the containers, and so on. We also distinguish 2 types of virtualization: a full virtualization. In a full virtualization, a guest doesn't know that is actually running in a virtualized environment. That means to a guest or a guest operating system, for that sense, this virtualized environment actually looks like hardware. And the all of the hardware devices and everything that is accessible to that guest, and it's the host who actually provides, so makes these accessible. Look to the guest like hardware devices, and the guest uses its own native hardware drivers to actually communicate and use these devices. And that's done through a translation software layer there. Often the host then emulates certain hardware devices, standard hardware devices, such as network drivers, disks, and other things. And then there's the concept of power virtualization. In this case, the guest OS is actually adapted to run inside a virtual environment, and it uses specialized power virtualized device drivers to communicate actually with the devices. And there's different methods to do this, different implementations. Some hypervisors implement their own version of power virtualization, but there's also a standard for it, and it's called VirtIO, and it's published by OpenOasis. And the standard, I think, it's in its version 1.2, 1.3 now. It started out, of course, with devices. All of this virtualization essentially started out in enterprise computing. So the first virtualized devices typically were storage and network and CPUs. Because that's what you normally typically have in an enterprise computing environment, and to virtualize. Then, of course, displays eventually became standardized. GPUs became standardized. Sound now has a virtualization architecture, and so on. So it's continuously growing the list of. So keep emails here. Maybe I'll pull this down a little bit, get it out of the way. Yeah, a list of virtualized devices and standardized virtualized devices is continuously growing. All right, why would you want to do this in embedded systems? Yeah, well, I mean, it's the same like in enterprise computing. Resource utilization and sharing is important. Now, I have a quite intensive background in the automotive industry, developing head units or infotainment systems, essentially. And most recently, there's more trend in the industry to actually integrate more features or more things onto one hardware to get better hardware utilization, and potentially also well, to reduce the number of hardware systems, hardware devices, or electronic control modules that are in a vehicle, as well as save costs in the process of it. And what is now has become commonplace in the system is like not only have an infotainment system, but have what's called a cockpit domain controller. We integrate essentially the infotainment system as well as the instrument cluster and other functionality into one system. And that is often done using virtualized systems, essentially. And maybe that one company may have actually been setting that trend of higher integration, maybe Tesla, essentially, who actually started out creating that central computer controller that actually controls pretty much most of the function of the vehicle. Isolation, yeah. So you in a virtualized environment, you can separate these running environments from each other, and the processes and programs that are running inside of them. Security is often also a consideration, which goes together with isolation. Although one word of caution here, virtualization by default is not a security concept. You still have to do work essentially to keep your systems essentially secured. Virtual machine is just that, another machine, and can be like a hardware machine. And if you don't, that's running maybe an operating system or a container. And the same as if you have a hardware and operating system running on top of it. If you don't harden it, if you don't apply security principle, it is not secure by default, even if it's running in a virtualized environment. Our virtualization also allows you to have different runtime environment. That's also in particular in hypervised systems, where you can say, well, you know, one virtual machine runs a Linux environment, another virtual machine runs a different operating system, such as QNX, a common example from the automotive industry. Virtualized system also can help support with the system lifecycle management. You can bring up virtual machines and shut them down individually while the host is still running as you want. It can help with system startup and shutdown performance. If you say, well, this virtual machine that we need maybe for the instrument cluster, automotive example, needs to start first, or in a other environment, we need something that starts quicker to show maybe cameras or things like that, and other things can be deferred until a later point in time. And of course, it can help with some software updates, because you can update the virtual machines individually as an entire system. And of course, you could have more granular software updates to inside of the virtualized environment too. All right, next slide. So what is a hypervisor? So hypervisors are provide virtualization environments that can run entire guest operating systems. It allows the guest operating systems running on the same hypervisor can be different. So it can be a Linux system and that can run next to a Windows system. And you may be probably familiar with it if you have used something like VirtualBox or VMware or so, where you have a host system. Maybe it's a Windows desktop that you're running, but then you want to run a Linux system inside of a virtual machine. And you can, of course, run also other operating systems there. So the hypervisor virtualizes CPUs for its guest environments. But of course, it virtualizes the same CPU architecture as the host is running on the CPU hardware, essentially. So if you, what's typically you're running now an ARCH64, not ARCH, x86-64 environment on your computer, then of course all of your guests are also running x86-64 CPUs. That's what the hypervisor virtualizes. And yeah, we distinguish here for two types of hypervisors. A type 1 hypervisor. The hypervisor actually runs directly on the bare metal hardware. So there's no operating system involved. The hypervisor boots up, and its job is essentially, and the only thing it does, provides the runtime environments for the guest virtual machines, typically. And yeah, it runs on a typically some sort of a kernel, but then everything that's that the system provides is really dedicated just to virtualization. There's no other functionality. This typically also is commonly referred to as the domain 0. Examples for that are Linux KVM, kernel virtual machine, Citrix, Microsoft Hyperdrive, and Xen, the QNX hypervisor. And then we have the type 2 hypervisors, where the hypervisor is an application program that runs as a process on top of another operating system, and in parallel to many other processes that this operating system could run. Typical example for this is VirtualBox, VMware, QEMU, virtual PC. I'll get into QEMU a little bit because QEMU can be more than just a hypervisor. All right, here's this like illustrated a little bit, type 1 hypervisor and type 2 hypervisor, what we just have explained. On the left side, type 1 hypervisor runs directly on the hardware. Type 2, you have a host OS, and the hypervisor is an application essentially that runs next to other applications on the host OS, and then the hypervisor provides the virtualization environments to the guest virtual machines and the guest operating systems. Next is an emulator. An emulator is a virtualization host that actually also allows to run entire guest operating system like a hypervisor. They commonly run as processes on host operating systems, similar to like type 2 hypervisors. But they also can emulate different CPU architectures. A common example for that is actually QEMU. So you can actually, so your host system is an x86-64, but QEMU can actually emulate, let's say, ARM architectures, and actually many other architectures, AH64. And that's actually what we're going to be doing in this class too. And if you have attended other classes, I think we're all using AH64 virtual machines running in QEMU. Examples of that is it's QEMU, Wine, an Android emulator does the same thing. And last but not least, container runtimes. So you could also say a container runtime is similar to a type 2 hypervisor. It runs as a process on top of a host operating system, and it provides the necessary runtime environment for the containers, for guest containers. However, in distinction to hypervisors, a container guest does not run its own operating system kernel, but it uses the operating system kernel of the host and its low-level libraries. So a container doesn't boot a kernel, but it essentially provides what is referred to as the, let's say, the user space, essentially. Typically, a container often doesn't have a system lifecycle manager such as systemd or system5 init or so. It simply has a runtime environment, and then you directly start any processes that you would want to run this container to run. Container guests are built for specific platforms, so they are targeted for specific operating systems and architecture combinations, and they share resources through their host operating system kernel in the same way as applications, regular applications would do, running on the same system. And you can have a container that just runs one application, one program, or it can run a compute operating system also as user space stack, sans or without the kernel, of course. User space stacks. All right, here we go. Linux containers. So Linux containers have been around for a while and have evolved quite a bit over the time in the technologies. And they are in general based on what's called the control groups, the C groups. So C groups were introduced by Google into the Linux kernel using the name process containers. Eventually in 2007, the nomenclature was changed to avoid naming collisions with other meanings of the term container within the Linux context. So it was changed to control groups. And then they were merged about a year later or so in January 2008 into the Linux kernel. So what do these control groups, C groups, actually do? They provide this functionality that are actually vital for running containers. They provide resource limiting, so you can set these groups not to exceed certain configured limit, memory and CPU usage and quotas and things like that, and CPU sets. You can set up prioritizations where a group or some groups have a higher priority to run on the host system, on the host kernel than other groups. Of course, important always, you can do accounting, so you measure group resource usage. Also, control, you need to be able to start, pause, stopping, restarting groups of processes. And also very important, the isolation aspect, isolating actually processes that run in a group from actually processes that run into another group, and even processes, of course, also that run on the host. All right. Now we're looking a little bit at the container runtime stack and how these things actually build on top of each other. And I use some Docker there. There's other container runtimes as an example, and we'll get into that too. And if you have used Docker before, you probably are familiar with that. So high level, you have Docker, the Docker daemon, and Docker, a command line process that actually interacts with the container daemon. And then there is an OCI, stands for Open Container Interface, an API defined essentially, that then launches the runtime process in which a container runs. And that is commonly for Docker runc. There's a couple of other implementations out there, each with their own advantages or disadvantages, and but they all kind of listen to the same OCI API. And then, of course, runc controls these containers. They're often also referred to as pods. You probably also have heard of Kubernetes, which is one of the container orchestration systems that helps you to manage large-scale container deployments, often also across many different hosts and hardware and things like that. There are others. So Kubernetes is kind of the first one that came out. That's the big elephant, essentially, or K8s. There's a smaller implementation of that. It's referred to as, so it has been developed by Rancher Software. K3s, there's OpenShift, there's Docker Swarm, Nomad. These are these orchestration tools, essentially. And on the lower end, of course, the lifecycle management, runc, that's used by Docker, runSC, and crun, and Railcar. There's also a couple of more. Some of these projects came up and then have been discontinued. If you're familiar with open source, then you know that sometimes that happens. It just depends on on the adoption of implementations. Okay. So far, so good. I've been talking a while now. We're getting a little bit of starting getting our hands dirty. Let's talk about the class environment and some of the conventions and the setups that we're using here. So this is, and let me stretch this out a little bit. So this is how our environment is actually looking. So you all have at your disposal a x86-64 virtual machine for Yocto Project built and everything that is hosted by DigitalOcean and has been set up by Michael Hosted and David Rayner for you guys to use. And that typically in these types of enterprise environments running a type 1 hypervisor. Don't know exactly what DigitalOcean is using for that. And so that's what, and then these, so we have these various Ubuntu lab VMs. Probably have now about, I don't know how many people here, but close to 150 or more of those running in DigitalOcean environment. And each one of you has one of those. It's Ubuntu running a Linux kernel. You have the libraries. We'll be running Yocto Project BitBake, of course, and things on those virtual machines, and eventually also the QEMU emulator that will emulate our Yocto Project system running it, which itself has a Linux kernel and libraries, and eventually the container runtime installed and container or containers, for last example, on top of it. Now the color coding here has a little bit of reason, and I'll show that in the next slide. Here we go. Since this is hands-on, we have quite a few commands here only that we're going to be executing. And all of the commands that you will be executing inside of your x86-64 build system, the one that's provided by or hosted by DigitalOcean, that's all in blue. So something like change directory to YP Summit, December 24, Pocky. Commands that you run on the container host, that is the system that's running inside QEMU, are color-coded in that yellow color. And commands that we eventually run inside of a container, they're in this red. And then when the slides have these gray boxes, then it shows a file content, and it also tells the name of the file. All right, so here we go. Now we're getting started. So you want to initialize your build environment, and you haven't done so. Now is the time to start actually working on this, and I'll do this. And if you can see this, let's see where am I here right now? Oh no, actually I'm actually not logged into my virtual machine right now. Let's do this. I need to find this password. This one. Oh, no. Here we go. Okay, so now I am logged in. So let's do this. CD YP Summit. Pocky. Here we go. The typical, you have to source your build environment. I typed this out. Of course, you can use the dot notation for that too, but that one easily gets lost. So here we are. And now you want to create a layer that is called a meta USB class. Just by running bitbake layers, create layers. Since this is my environment, so that's already created here. If you don't have it, so create that. And then there's a build configuration. Of course, bitbake layers, create layers will add this layer automatically to your BB layers setup. And let's check the build config layers. So that should be here after you're done. You should have this bottom line there, home iLab 1 or whatever your machine is called. And the user space class should be added to it here. All right, that looks good. And let's look into our local.conf. And These changes are all at the bottom. So David and Michael have been setting up this already. Should be all there, class configuration. So we are running, our class machine will be a QEMU emulated AR64 system. This is also already pointing to a shared state cache that's already filled, so it will actually speed up some of the build process here. Same with the download directory and a couple of other warning appends and things like that. And other things that we need actually for our environment here. So we need virtualization. We need, although we're not using IPv6, but for some things to build and work, we need actually IPv6 enabled. Yeah, the secure compute environment, and well, actually K3S we don't really need, but that's, yeah, and some other things. So if this looks good, we move on to the next slide. Our first little example or foray into the world of containers with Hello Containers. And to run containers, we need a couple of packages. We need container runtime, and we were using containerd open containers. We need a container command line interface, and instead of Docker, which is certainly the most common one, we're using Podman. There's a reason for that. Podman doesn't require a service to be running. It is just a simple command that you run on the command line. It doesn't need to connect to a socket and all these things. In my deployments of containers in the wild world out there, I found Podman a better choice to Docker. But of course, you could use Docker too on your embedded system or in your system that you build with the Yocto project. There's no problem with that. We need IP tables. There's network routing and filtering and stuff going on to and from containers. We need container network configuration, and we're using NetArc here because it integrates, actually, it's very tightly well integrated with Podman. CNI, the container networking interface, does work with Podman too, but it does not have intercontainer DNS enabled, and that's something we need for our last example. We need a couple of additional kernel modules, so we simply throw all the kernel modules onto our virtual machines, and we also to be able to test out and fetch containers from an upstream registry. We also need the certificate authority, the certificates available on the system. Okay, how do we do this? Pretty straightforward. You create a recipe for an image. We call it core image container host. We throw it into our meta USB class recipes core images directory there, which you have to create first, of course. It's there, and this is the content. So depends on how you're feeling today. If you're feeling like typing and doing stuff, well, you can type this in there. If you don't do that, you can simply copy it from the sources that are provided. And once you have that, we start running. And I'll switch over here to my terminal window and actually stretch this out a little bit. Why not? We still have some more screen real estate available to us. Let's do that. Okay. Good old bitbake. And I don't do this. And I'll just be building the container host here. And it starts running. Okay. So is this to some extent pre-built on my virtual machine already? It may take a little bit longer for you guys. And I actually somehow lost my... Oh, every time. 5%, of course, then I'll do my chat out here so I can actually see the chat window too. I neglected the chat, but now it's the time. Yeah, still IP tables in this thing, not NFT tables, but NFT tables are an option too. Correct? Yeah. Podman also fully implements the Docker API, so you can easily transition to it, and it is very much feature compatible to Docker, even the command line and everything. The commands are the same. Well, no, automotive does not want Docker on embedded. I haven't seen that yet. But what automotive does is actually typically running hypervised systems. It is common to use the QNX hypervisor, a QNX real-time virtual machine for the instrument cluster, and a Linux system for the infotainment. Yeah, okay. So what's my take on the impact of virtualization containers on real-time latencies? Well, I haven't deployed a container on a looking at a hard real-time system or so, even not with a real-time, like even not with a Linux real-time kernel. I since the once the container is running, the processes inside of the container actually run on the host system. I wouldn't necessarily expect any latency increase over the host system, or executing a command directly on the host system. Yeah, well, you're right about my email client, so I'll kill it. Also, it's quiet now. Should have gotten this. There we go. Okay. Yeah, Blue is the build host, the VM from DigitalOcean. Blue is the ocean, exactly. All right. Yeah, well, latency may increase with the overlay file system. Yes. Well, you don't necessarily have to use the overlay file system. You can configure it actually differently to not use overlay file system, but for the different layers of the container. There's one question: how does this compare with KS? I yeah, maybe I don't understand the question, but I don't have the answer for that. Okay, I don't know how you guys are doing, so mine's almost done building here. Oh, set scene, yeah. Oh, good. Building Rudolf, so we're getting there. Good. Thanks for the feedback. Appreciate it. Okay, well, rootless Docker is now possible. And so I'm not quite sure about the status of, well, Docker CE, which is a community edition, being used by Meta virtualization. What the status there is. I stopped actually using Docker about a year ago or so and switched actually everything to Podman. I used actually a nerdctl for a while too. But it's not as quite feature complete as it is to Docker as it is as Podman is. So Podman now has been my go-to on both sides actually for building containers with the Yocto project from upstream repository or using Docker or Podman Compose as well as on the runtime. Okay, yeah. Okay. Yeah, I thank you for the response. If only on the cows cam. I have no experience with that. So, all right, I'm done building. Now we can actually run our emulator here. Which will ask me to enter my password again. Let's see. I think I still have it in there. Yeah, that was good. Now Quemo is starting. And to see if everything is working, we're actually simply using Podman to pull a BizBear container from actually an upstream registry and then simply run it. And of course, it's root with no things. So yeah, just let me know what your status is. We need all to be kind of at. I mean, of course, a lot of people here, and ideally, most of us are on the same. Eventually have this build. This initial build will take a little bit longer, and then subsequent builds. So we're just running these. Yeah, so we're adding the raw network capability to it simply because we're using ping inside of the container, and ping is ICMP. ICMP is not by default a capability that's now provided by the container runtime environment, so you have to explicitly add that. Just do BusyBox. To do this, Podman starts up, and it will give you actually, so Podman, when you run it like this, it'll actually give you a list of repositories from where you can actually grab this BusyBox, this container essentially. And Docker.io is of course the old and known. Just hit enter to do this, and then it tries to pull this container. Okay, to create image SBOM as PDX. Okay, you're almost there. That's good. rootfs, still take a little while. Good. Okay, so here we are inside of this container. Start it up, and now you can, of course, poke around here. This is the container just running BusyBox essentially, and see if our network is working. But that is important. We'll be using some of that later too. All right, here we go. And I'll hold on. Yeah, of course, it's difficult for me to judge where everybody is in this process. I can just hold on for a little bit longer here. We can done building. Okay, starting Quemu. Thanks for the feedback, guys. Appreciate it. I'll add some thumbs up here now. Good. Okay, we're starting, done building. Okay, we're getting there. Able to Bing. Yeah, good. View image. Okay. Almost. That takes a little bit. Starting BusyBox. Good. All right. Yeah, we'll give it a couple of minutes. I mean, all we have, well, 1.5 hours, but we already spent 45 minutes. Okay, more good. And of course, well, let me mention that all of that is available to you too. I mean, of course, you can eventually take it from your virtual machine, but it's also uploaded the slides as well as all of the scripts and recipes and what else to the to the pre-talks website attached to the to my presentation. So you can at any time, recreate this and of course play with it, extend it, whatever you feel like doing. Rudolf 88%, all right. Yes, Docker IO has container images of multiple architectures. And Podman, if you run it on a system, is actually, of course, I'm also able to detect what architecture it's running on and to pull the right images. So this is actually seamless in this case. It gets interesting now. Later, we're going to be building containers using an upstream registry, and then we have to tell, of course, Podman what architecture to pull. Otherwise, it will actually pull the host architecture, the build host architecture, x86-64, and that will not run on a AR64 system. Building, good. Running QEMU. Yes, I appreciate all your feedback. Thank you. That actually helps a lot. So I'm used to, of course, well, before the virus hit, but still yet a lot of these presentations and training classes I've been doing on the Yocto project, and it's often, of course, it's in person. And of course, if you're in person, feedback is more immediate than it is in this entirely, let's say, virtualized environment. Pun intended here, I guess. Looking good. Successful build and run. So, BusyBox ping works. Excellent. Okay, I guess I'll get the feeling that most of us are probably there. And so now you can exit from your container again, which are actually terminated too. And then we can, of course, shut down our emulated QEMU system. Good. Moving on, if that's okay. We've got some more material to cover here. Okay, next exercise is we are building a container. So we're building a container image with the Yocto project, and then we are putting it into our host system, and then we run it from there. For that, the meta virtualization layer provides the image OCI class, which facilitates building these container images, which is great. It creates a tar image, and that is compatible with the Open Container Initiative, OCI image specifications. So you can run it, of course, then with Docker, Podman, and the likes. You can load this image, Docker, nerdcdl, Podman, and so forth. And we inherit this class, as it is typical with the Yocto Project classes, by the recipe, and you configure it through a couple of variables. And then you want to add, well, the packages for this, for your container image are added as usual to using the image install variable. I'll give a short overview over these variables that you have to configure the image OCI class. So there's an image author. Well, that is the name of the author yourself, and it uses that default patchkit username. If you have set that, and the email address, every time you build a container, it is tagged essentially with a tag, and the default there is simply latest, which is common. You can give it a runtime user ID, for which there is no default. The OCI image architecture, it is typically the target architecture, which is what you want. In our case, it would be AIRSH 64. There's a sub-architecture that is derived as such, the default from the tune features. An image entry point, and a container has an entry point, which is the process that is started when the container starts up, when it launches. In this case, it is, the default is actually just sh shell. And you can, of course, also provide arguments to your entry point command. There's a couple of more of those. The image working dir, that is where the entry command is actually launched, so it changes directory there. You can specify a stop signal to terminate the container. You can specify a list of ports already that you want to have exposed by your container to the host. And you also can create a couple of more labels that you can attach to your image and environment variables in this format. We're not using, in this example, all of that. We're taking it a little bit easier to start off with. So here is our container recipe. And this is also an example that is readily available on the Metro virtualization layer. We are actually running a Flask application, which emulates a small like web server environment. We tag it as some Flask demo. As the shell, we're using BusyBox. Our image file system types are container and OCI. Of course, we're inheriting our image OCI class. Source is unpacked. That's where now the source is getting unpacked too. We don't need any particular image features and linguas and things. You could add those, similar as you would do for if you're building a bare metal system, essentially with the Yocto project here. And we're adding base files to it, password, netbase, and the container shell. And then, of course, we want to our Hello World Flask application that is part of the meta container, meta virtualization layer. Sorry about that. And we are building without a specific kernel in mind. It is a container that's going to be running on our QEMU system. So that's the container recipe. Then there is an image recipe that, of course, then builds our QEMU image again. Yes, of course, you can start a Ubuntu 24 guest with Podman. It's all good. Works. Okay, so typical stuff. That's mostly already there from our previous example, from our base example. Or the only thing we have to put this container into our image, and we're just doing this with a rootfs postprocess command. So essentially, from dir. So we our Flask container actually copies that container into our deploy dir image, and from there we are copying that tar ball into the image root.fs, simply into the data there, which is user share. And of course, then you have to add your post-process command to the list of post-process commands. And this is it. So if you're familiar with that, that's the standard Yocto project stuff. Okay. Here are steps to creating and building, and I rested this. You just walk through this. My application has this already set up. And you just let me give you your feedback. You're actually building the container first. So that's our container here. And it may already been built, but you also probably have it in the shared state cache, so it should be reasonably fast. While the post-process command, uh, yeah, I mean, you could with the recipe, you could package your container and then into an archive, into an RPM or whatever you're going to use, and then have it installed that way. Yeah, that is possible too. I'm going to fail to find root fs. Did you build the um oh, okay. Did I miss something here? Did you copy the container image, core image container host flask, and bitbake the container? Well, the container host. Well, this should actually say, sorry about that. That's a typo. If you copy, so if you copy the image recipe, actually, from the source directory, it has a dash flask appended to it. So you would actually have to do bitbake core image container host flask. That is my mistake. No, just do what's now on my terminal here, bitbake core image container host flask. That should be fine. Because what you're doing right now is yeah, I worked with these slides about 4 times, so kind of missed this piece. Eventually, if you do it something multiple times over and over, you just see what you want to see, but not necessarily what's on the slides. So my bad here. I mean, alternatively, instead of copying it, you could simply change your core image container host and add these lines to it here at the end. That will work too. And then once it's running, we can run this. I mean, I could say I purposely make these mistakes on the slides to keep everybody awake during my presentations, but that's not the case. Oh, okay. So the recipe files and everything's already present. So you already have the complete meta USP there. Yeah. Good too, I guess. Michael imaged the entire master image pretty much, except for the TMP directory. That's why I have to restore from shared state cache. And it takes a little bit here and there. Yes, you can make containers start automatically at boot time. You can do this with systemd service file. So I have done this. It's a deployment that's actually at one of my customer sites. Um, well, yeah, there's multiple use cases. That's an example from one of my customers who I developed an embedded containerized systems for a telematics device. Actually, not for telematics device. It's for a service tool device that they're using. And they're running actually. They have an application that's with a web interface that runs their service tool essentially, and that's in one container. And then they wanted to add because that is a simple web application. It doesn't have any security or any certificate checking or any of that. So they wanted to have another container in front of that reverse proxy, which is an example that we're going to be doing later with Nginx to do that. And so that was one of their reasons to do that. But they also wanted to be able to say, okay, they have over-the-air update mechanisms to update the entire system, with a dual bank term system, which are developed for them. But they said, okay, we don't always want to update the entire system. We just want to update, a piece of it. But we also want to be sure that we can roll back. So in this case, what would change most frequently for them? Well, that's their web application probably. So they put that's in a container, and then we simply can update the container and then start a new container. And if something is not working, we can actually just fall back to the previous container. So that's their rationale. Included image built by include, yeah. You could do that. You can put it as a dependencies in your image install. You could kind of work this through and say, okay, well, to my recipe, I'm now adding a packaging and a packaging uh, task, essentially. So I package it as RPM or whatever it is, and then I install this RPM when I'm doing the image process. Yeah. Yep. All right. We're almost there. Yeah. Podman and Podlets. Yeah. Create service files. We can use those as a starting point. I'm building. Good. Well, so am I. So let's move on here. Running Quemo again. So once you have a load, okay, so you can, of course, check if your Flask demo OCI, if that has been installed. Should have been. And then the next step is first we're loading the container, tarball, extracting it, so make it a runnable image, essentially. And load minus I, user share, Flask container, and so on. It shouldn't take too long. All right, there we go. With Podman images, you can, of course, verify that your image has been loaded into the Podman registry there. And now we're running this Podman run. We give this container the name Flask once it's running. We're running it in the background, and the image that we're running is called Flask demo, as you see here, Flask demo. All right, here we go. Podman starts up, sets up its network. That's why you see here these these messages from the kernel. Sets up its network connections, and now it's back. The container is running, and now we can see if we can actually get a response from our little Flask server inside. So the Podman has a default container network that it sets up, and it starts with 10.88.0, and .1 is actually the host itself, and .0.2 is the actually first container running on the system. And this Flask service listening on port 9000, and then there's two subdirectories called one is Yocto and one is OE, and it should respond here and give you a hello from Yocto, and then you can change the last thing here. Don't go back here. Oh, really? And here, get a response from Open Embedded too. There we go. Can connect. So is your containers actually running on your system? So if you have started the container, so you can actually check if the container is running on your system with Podman container ls, and it should actually show you a running container in this case, yeah, that it's up. It's all a little bit scrambled here. All right. Okay, yeah, that means that it's running, but it should be responding too if it's running. Okay, yeah, Podman PS, you can list the running containers. Should come up. Okay, now it worked. Perfect. Very much. So we're running this container in the background, and you can actually attach to this container and poke around in it. Just an information, that's a typical, nothing to do with the Yocto Project, it's a typical Docker thing, execute a command inside of container. So Flask is the container name, and then we want to execute the shell. So here now you can actually poke around and say, and here you see that your Flask app here is running. That's a Python 3 application, of course. Good. All right. Having some success here. Perfect. Get out there. If you want to get rid of your container and shut it down, Podman kill Flask. Done. So the network gets shut down. All right. Init 0, shut down the thing. All right. We're doing good in time. Good sales pitch for Podman as a replacement to Docker. Okay, yeah, I'm hooked on Podman. I admit it. Actually, I like it. And it works for me. It worked for me. Of course, for this presentation, it works for me in an actual application, so I don't have any complaints about it. There we go. So I guess the Red Hat people are happy with me here. Okay. If we're all good, having this, I'll actually have a sip of coffee, and then we step onto the next thing. We're embedding containers that we're pulling from a registry. The question is, of course, why would I want to do that rather than actually building my containers with the Yocto project? One reason is there is a lot of ready-to-go containers already available, and why reinvent the wheel if somebody else has already done it, such as some Docker.io registry and others. And no organizations, companies, they build their own containers and maintain their own container registry, and they do it. Said, okay, well, maybe based on upstream, maybe created from scratch. Who knows? But they say, okay, well, that's what we're doing. This is our work. We want to have this on our embedded system. Or, I mean, you can build other systems, not just embedded systems, with the Yocto project too, of course. Another thing is, of course, you can leverage developer workflows that are already familiar with using container-based systems, and they develop stuff in containers and put it all together, and they don't necessarily have any Yocto knowledge. And they say, okay, well, we do this, and we have our own registry, so we want to use those containers. Our two directories, image and images. Should be images. Maybe that was a mistake that I made in the original one. Let me see. I actually didn't realize that. Oh yeah, there is image. And is there images? Okay, well, I don't have images, but I have image. Yeah. So mine are in image. So I don't know how that happened. Maybe a mistake I made. Apologize for that. The only disadvantage, let's say, if you have, you don't have the Yocto project support for container manifests because you're using containers that are created somewhere else, provided by somebody else, and if not yourself. So you have to be aware of anything that has to do with the manifest, what's in there, and the license checking. Yocto project, of course, does that for you if you build your containers or build any system with the Yocto project. So these are nice tools available for you there. Okie dokie. Now we're using the Podman tools, not just on our emulated system, but on our host system to actually build our container. And so I have to continue my Podman sales pitch now. Why do we do this? Podman, first session task, confirm. So it's just stopped at 46%. And it's not moving anymore. It's moving, but it's terribly slow. That is, yeah. Well, I don't know. You could try to interrupt it and restart it. See if that fixes the issue. Well, that's on all pure bitbake stuff. Bitbake doesn't throw currently 4 running tasks. Yeah, whatever tasks are running. Thanks, Mike. Appreciate it. Okay, Podman sales pitch. Rootless architecture, so it's easy to run and integrate. There's no central daemon required. It does have a Docker-compatible command line interface. And you store the images locally. It actually allows you, Podman also, you can define a root directory where to create your images and where to store them. And you can make that also relative in your build environment. We're not doing this right now. It's kind of a little bit more an advanced topic to do it that way, right? But I typically do that. There are some prerequisites necessary for that, but it's already done for you. You have to have Podman installed on your system, running bake, and you can find instructions on how to do that following this link. And yeah, and Podman then carries out certain operations inside of the recipe. We're pulling images, and here we actually have to specify the platform, operating system, and architecture, and from what registry we want to pull from. So the registry name, the URL typically, the image name, and an optional version. If you leave out the version, then the latest is going to be pulled. And then we're saving the container image archive, and then actually include it into our root file system. How do we do this? Here is the recipe for it. And I use a couple of variables to make this maybe a little bit more transparent. Container registry, that's where we're getting our image from, Docker.io. The image that we're pulling here is our BusyBox latest image. We give the archive that we're building, we give it a name, which is called container images tar.gc. And container install there, that's where we install it eventually into our root file system. And here we're actually using the root file system to install a package with our container. And all the magic happens here in do create container. First, we determine our architecture we're running on in a format that can be then digestible by Podman. And I spelled it out a little bit to make this more clear. So we need to determine the architecture. That's pretty straightforward, the target architecture. But then we also have to determine the target system. And we're getting that by actually using target OS, and then we have to just take the first field. It is how the registries are actually requiring that information, and then we put this all together in this way: first sys and then architecture. So we like Linux ARM64. Here we go. Podman pull platform. The platform that we defined here, container registry, and our container name from up here. And once that's done, we create the archive. We just put it together. And of course, we add, this is a new task, create container. So Yocto Project Bitbake doesn't know about this, so we have to add it. And do install. We have to enable actually container the networking inside of this recipe because we're pulling actually from a outside registry. And do install, so we're simply installing our container into that container installed here. And as such, it's going to be packaged then by Yocto Project and installed onto our target system. That's it. Is there a minus native variant for Podman? You mean like building for a build host? If that's the case, you just have to omit, don't specify platform, and then it determines the native whatever build host you're running on by itself. How friendly to using read-only file system on this is? So you want to on your target system, you want to use a read-only file system, essentially. Yeah, you can do that. That is not a problem. You may have to. So typically, then the container runtime environments are actually stored in /var on the system by Podman. You can install them somewhere else or have them. This is all flexible. That's what I typically do. So there's a lot of things you can actually parameterize to your liking. So you can have your container, you can have your root file system read only. Not a problem. All right, here we go. So here we're doing this. This is the recipe. It's called simple container. It should already be there and everything. Here you can either add the recipe to the container host image, but there's also an image available that's called core image container dash host dash simple, and you can build that one. So just do this. Is there a way to get container images pre-installed? You don't want to go through the load command. Yes, it is possible. You can do this with Podman. You have to package up this entire um, uh, registry essentially that Podman creates and install that on your system. I've actually been doing this for a customer, and the very reason for that, why they're doing it, is because they wanted to upgrade systems that originally didn't have any container tools installed, so they wouldn't be able to run Podman load. And they first wanted to upgrade, put the containers on there, and then upgrade the rest of the system, and then on another bank, and then flip it over. It's a little bit more involved. All right. Just asking a bit feedback. If you guys are building this, if it's working. Yes, you could do it too. Then the install command, and it runs on the first startup of the system. That is correct. But once you have done that once and your on-target registry is filled with your container images, you don't have to run this command again. So you only have to do the load once. Uh, multi-layer meaning that multiple layers of a of an overlay file system. Yeah, it does that by default. The recipes, yeah, they are on pre-talks too. I uploaded them. Oh, this is so big that I can't see it. But I put them there. Let me see. Yocto Project Summit. Here we are. Here. Got now a little bit big. Yeah. Here are the recipes and other supporting files. 40 kilobytes. They're all there. Okay. Well, you're ahead of me. You're done building, not mine. Stuck there. If you're done building, I'll just scroll ahead to the next slide. This is what you're going to do then. So you can check, your container images should be there. You do use the podman load command again to load your image, and you run it. Okay. So what this is essentially, so we have what we did in the very first example, but in the very first example, we pulled the container from the registry at runtime. Here we actually pre-building the container and loading the container onto our system image through the recipe. All right, here you go. Mine is almost done too. Get the license information right. Oh yeah, thanks for posting the link. Yes, you are right about that one. That Podman is actually at version 4 point whatever something, and the latest version is 5 point something. Actually, in the latest version of Podman, there's a fix in them that in it that actually I initiated earlier this year with them. It had to do with the how long the paths can be for the that you specify with the root directive to Podman. And in most instances, it was never a problem, but it's a problem with the Yocto project. If you want to put one Podman to use a root directory that's inside of your Yocto project build environment, and these paths can get actually pretty long, beyond the 128 characters that they originally had defined, and that is fixed in newer versions of Podman. I had to patch mine to make this work. So okay, we are running Qemu again. Yeah, for the container host, you would have to actually change it to work. You have to add the recipe to it. Now I lost my mouse pointer, so copy my maybe passwords here. Okay, so our container image should be there. It's called container images. So here we go. And we load this. If everything works correctly, and we did it right. We should be able to load this. Podman's going to be happy with it. All right. Not loaded, I would expect so. Here we go. We've got our busy box that we pulled from upstream, and that is no different from what we did in our first exercise. The box latest, why you can actually omit the latest. Oh, I did it wrong. Podman run. I wanted to remove the container after. All right, here we are, and see if our Yocto Project website is responding. There you go. All good, everybody? Out of this container and shut down my Qemu emulator. Oh, we're out of time. Oh, I thought we had until 9. No, it was 1.5 hours. Okay. I think what is actually next in the thing? I mean, if you guys, I'm happy to continue through the break or on if you like to. I don't have a problem with that. I guess I've been talking too much, or the building takes too long. I'm blaming it on the building. If you guys are okay, we can continue. So we have 2 more things. So this is okay. So the one thing is, of course, the next thing would be building containers with a Docker file. Who wants to use plain upstream containers? Yeah, sometimes, but not always. So the first step is now we use a Docker file to actually modify our container, essentially. No break, okay. +1. I'll take that as enough of a vote for now. Let's go. Let's do this. Okay, what's a Docker file? Well, if you have been using Docker, you know that it's a text file. You have instructions in there for building Docker images. It's a step-of-step commands that then the Docker or Podman, for that matter, uses to assemble your container. And it typically starts with a base image, and then you add more stuff onto it. Okay, perfect. Typically, with copy, you add files from your local file system to the image. You run, you can execute commands there during the build, and you can specify the default command to run the container. And we are going to do this. Here is our Docker file. It's pretty simple. We are using the latest Alpine image, and we are just adding NCAT to it. We are exposing port 2000, and then we run this command, which simply implements a little echo server using NCAT. Pretty straightforward. And here's the recipe for it. Yeah, I need to go deeper. All right, good one. So things are pretty similar to the previous recipe. We do create container. It changed a little bit. So first we're pulling that image. Of course, while we're pulling and building this image, and this time we actually specify our Docker file that we're building with. And of course we're doing the platform. And then we package all of this up again and put it onto our root file system. Jumping ahead. So, well, you can do this container host, but there is also another image recipe there, and it's called Docker file. So if you run this on your system, bitbake for image container host Docker file, it will build your next image for this class. Yeah. You wouldn't, so load Qemu use a static image. That's the thing is now when you're building this project and we are installing things onto, so we're running APK add inside of the container. And we have to do this with ARM AR64 architecture. And the Query user static actually fetches this image essentially and makes this possible. That's what it is. But it's actually should already be set up on your system, so you wouldn't actually, we don't have to do this. But if you do this, redo this entire thing with a new system at home, you would have to run this command. Thanks for reminding me of that. It does fail. It could probably fail because it's already installed. So it should work out of the box, just running the core image container. So I don't know what the error message is right now. Okay, so yeah, the exit container form, that actually means that you actually should run this command, sudo podman run the multi-arch, the user static command, because then that is that error that you get. You have an execution format error, which means it tries actually to run an x86-64 on this Docker container, which doesn't work. Short name, you did not resolve to an alias and no unqualified search registries. Okay. Yes, in this case, yeah, it depends on this container is actually installed there. But I'm not sure. So it didn't find the registry. Oh, okay. That's actually don't know right now why that is happening. Let me see. I'll see why this would be happening. CP Docker paths have an extra user space. Okay. Yeah, should be. Let me see why this is not doing it. Not large. Yeah, I don't see why running the multi-arch thing would fail. It shouldn't even be necessary. So even if you run the command, it actually should, yeah, it just runs and sets up the environment for it. So I'm not sure why it would fail. And since the virtual machine actually has been cloned from the master virtual machine, you wouldn't even have to run this command. But even if you run the command twice, it has been run before, it doesn't cause any error issues. Okay, I don't know how building process looks for you guys. Mine is almost done. All right, it is done. As usual, we start Qemu here. Once it's up, we load our image. I guess we have a couple of minutes left. I have one more thing. I don't know what is actually happening in this room after this presentation. So we've shot our Echo server container. Now we actually have to, yeah, look. Oh, no. Have to load first. I'm getting ahead of myself here. Oh, okay. Oh, pitfalls and upgrading. Okay. Well, then maybe this may just be the last exercise we can all work through. I can talk through the slides a little bit to finish this up. So running our Echo container now. Oh, Podman, well, forget the run. It won't do anything. So now we're starting this container, we're detaching, which means it keeps running in the background because it loads its echo command there. You can go into the container and check if the process is running, or you just do this now with socat from standard input TCP4 10.88 on port 2000. So now we're connected to our Echo server. So do like no, it's not echoing back. Why not? Ah, no, of course. Nobody told me that I'm fat fingering all this thing. Here we go. Okay. All right. So we're running out of time. The last thing here is we're building containers with Docker Compose. Now, Docker Compose allows you to build multi-container environments together. And these are the key features. And I have the recipes and the details in there. So we're actually doing a multi-container environment. We're using a web server with a reverse proxy. So we're using LightPD in a container as a web server, and we put an Nginx container essentially in front of it, which actually then takes all the requests either on port 80 or on port 443 HTTPS and forwards it to port 80 on our LightPD container to answer the responses. So there's a compose file for it, and if you're familiar with those, this is there's a special structure, essentially how they work, but it's pretty straightforward. We're defining two services. One is called LightPD and one is called Nginx. LightPD, we call it the web server because the name of the entire deployment is called web server. We call this the web server LightPD version 01 container, essentially. We give it a container name. Actually, well, this is a copy error. It doesn't have to be privileged, but that's fine. And we're building it in the context of LightPD, and this is our Docker file that we're doing there. And we do something similar with Nginx, where we actually are building an Nginx container, which is readily available from upstream with this. And we're exposing ports 80 and ports 443. And we're also using for Nginx entry points to use the local resolvers, because our Nginx container has to resolve the name of our LightPD container. Here are the Docker files for it. LightPD, pretty straightforward. It is an Alpine container. We're just adding LightPD. We're only adding a small index HTML file and hello world index HTML file. And yeah, and this is a command that we're running inside of the container. Nginx reverse proxy. We're using the Nginx container. We're adding a couple of additional tools for SSL, TLS. Validations. I created some simple set certificates, so they don't have the full certificate chain, but just to demonstrate how this works. And yeah, and then we have some Nginx templates that we need for the for the services of Nginx and the necessary port forwarding and everything. That's all standard Nginx stuff. It is all in the package that I provided there. The recipe is quite interesting. Of course, now we're using Podman Compose to actually use the compose file and to make sure that we're actually building for AR64. We have to pass our platform into it again, and then we use our compose YAML file to do this. It's 2 steps. We're pulling first, then we're building. And then we're creating the archive, we're packaging everything up, and we install it again. And then there are the instructions. And yeah, I think you could, we can run this. I don't want to take any more time of the following presenter. I apologize for that. I ran 2 minutes over into his time. So we'll break it here. And I'll give back the presentation. So thank you everybody for listening or so. My email address are in pre-talks and in the slides, so you can contact me if you have any questions. Everything is available for you to actually try at home too. Strongly encouraged to try it at home and play with it and modify it. So thank you very much. I appreciate it. Take care.